Next talk is by Himanshu, Badhani.
Hi. This talk will be based on this particular work with Subhashish Banerjee and Dr. C.M. Chandrasekhar. Let's start. So I would like to start with a good old classical random walk, where of a coin. So the coin, or somebody rotates a coin, or a coin rotates, and you get either a head or a tail, and depending on the result, the coin is moved either to the left or the right on one-dimensional lattice, right? So these are the two operations, the toss and the movement, and we can try to calculate what the probability distribution is after some time, and this is the graph I made in my first sem StatMath class, and you can see that the variance of this of such a walk increases linearly with time, right? But what happens when you give the coin the freedom to be in two particular states at the same time? Now, let's call the tails the 0 state and the heads will be the 1 state, and now it is in a superposition. And now you put your decision making operation on this superposition, and what you will essentially do is you will spread the particle over a lattice in a superposition, right? And so at the end of this, so you see that you get a particle or a state which is spread out on the lattice, and it also has a degree of freedom, which is we'll call it the spin or the coin degree of freedom. So it resides in a Hilbert space of a position and a coin space. Okay? Now, what happens in a quantum walk is that you have replaced the toss with a SU2 rotation. It need not be an SU2 rotation. If you have higher degree of freedom, you will have SUN rotation. And conditional shift can be written down as an operation like this. And this is just one of the example of a shift. Like this shift operation says that if the state is in 0 state, you go one step back. If it is in 1, you go one step forward. But you can have almost infinite number of such shift operations. And this shift operation is the one which is somehow entangling, or in some sense interacting agent between the two degrees of freedoms, right? And the walk operation as a whole is consecutive action of a coin and a shift operation, right? And you can do this walk multiple times on a state, and then you calculate the probability of finding the particle. You sum it over all its spin degrees of freedom. I'm calling it spin, the coin degree of freedom, and you can calculate what the probability distribution for this particle is going to be. And it turns out that the variance actually increases as t square. And it's here where this property of this ballistic propagation property of these quantum walks is very useful. And we use it just like a random walk is used in simulations and in algorithms and in many, many areas of physics. Quantum walks are being used similarly. There are algorithms which are quadratically faster, for example, search algorithms, which can be simulated using a quantum walk. And at the same time, quantum simulations is a huge branch of quantum information. Quantum simulations is a branch of quantum information which is blowing up, and it's because of the ease of performing quantum walks and the varied amount of systems that it can simulate just by changing the parameters of the quantum walk. As I showed you, there are SU2 parameters that you can tinkle with, and then you can also change the way the shift operator tells you to move backward and forward, and you can change the dimensions also. So in that sense, quantum walks and how it can be easily performed in a lab. The kind of quantum walk that I am talking about is you can have an electron with 2 degrees of freedom if you can somehow trap it, or you can use a photon if you can keep the coherence for long enough time, right? So you can perform these quantum walks in a lab easily, comparatively. Now, important aspect of these quantum walks when you're doing them in the lab is that you have to think about the effect of the noise, right? And what we know so far about the noise and how to model it comes from these particular two equations. The first equation is the stochastic evolution of a quantum state. It was developed in 1960s and 70s. And the second is the dynamical equation, which tells you at one particular time how the system evolves. I have highlighted the S in both the equations just to show that the S stands in both the equations stands for Sudarshan, and this being the IMSC's event, just to highlight that it has these two equations, which form the cornerstone of our understanding of open quantum systems, have a strong IMSC connections. Now, but that was not the full picture. Non-Markovianity is the kind of noise. Sorry, I think I forgot to mention that the second equation comes when you have Markovian assumptions, especially, and those assumptions are especially strong when you have, or they are valid when you can have weak system environment interactions. But that is not always the case. And evolution at a particular time can depend on the history of the state at some earlier time, right? And one mechanism for this is what this diagram is trying to show is that if the interactions are strong enough, the history of the interaction between the system and the environment can affect the environment at a later time. In some sense, it is the idea of information backflow, right? And this is one of the ways non-Markovian effects can creep in. And now we will look into a particular kind of a particular way of modeling this noise, which is the non-Hermitian evolution, but in particular the PT-symmetric non-Hermitian evolution. Now, in quantum mechanics, for closed system at least, we want our operators to be Hermitian, because hermiticity ensures that the results of the observations are real, right? So you can define them as operators, but the converse is not true. There do exist non-Hermitian operators which have real eigenvalues, and they are exactly these operators which are invariant under the subsequent action of parity and time reversal symmetry. Parity and time reversal operation. So these are PT-symmetric operations, PT-symmetric operators. So PT-symmetric Hamiltonians, for example, will have real eigenvalues even if it is not Hermitian, right? So where do we see PT-symmetry in nature? One of the most well-known areas are when in optical systems when we have equal gain and loss of amplitudes. There we see PT-symmetric, those systems can be described through PT-symmetric Hamiltonians. Right? And I like to see it as some sort of coarse graining, because if you're losing and if your source and sink are equal, through some coarse graining you can kind of go back and assume that there's nothing much has happened. No, there is no loss and no gain. But yeah, there's a more rigorous way to put it, which we won't do here. Now, there's an idea of pseudo-hermiticity where all PT-symmetric Hamiltonians satisfy this particular equation. Okay. So all the operators that satisfy this equation are called pseudo-Hermitian for some Hermitian matrix or Hermitian operator eta. And it was shown that if you redefine your Hilbert space by redefining your inner product in your Hilbert space, inner product between two states in this particular way, where you put eta in between the two states, through this redefinition you write down your Schrodinger equation or von Neumann equation. You get back the original equation where even if this H right now is non-Hermitian, you get this equation which is true only for Hermitian case, as we saw in the previous slide, right? So in some sense, for PT-symmetric Hamiltonians, one can establish an equivalence between unitary and non-unitary dynamics, PT-symmetric non-unitary dynamics. And now the idea is to extend it beyond PT-symmetry. And can we even do it, right? Can we find the slide shows that the inner product that we defined was the inner product that we defined can be written down as an inner product between, can be written down as inner product between this dual vector, which is redefined using the matrix eta, right? And that's why it is called a metric. Although, as to make it sound like this is like a space-time metric, but as far as I know, the analogy ends here, right? But it is but this metric can be found for a given particular H, even if it is non-Hermitian, and it was shown in 2019, right? So what do we do once we have a metric like this? So what we wanted to do is our system, as we initially talked about, consists of a position degree of freedom and a coin degree of freedom, right? And we are concerned in scenarios where the walk completely as a whole is interacting with the environment. And we want to find out how the coin and position interaction is changing with, due to this noise that the whole walk as a whole is experiencing. So we are interested in and because the coin space is small, we can study using numerical techniques easily. So we want to look at how the coin dynamics is changing because of the non-hermiticity of the walk as a whole, right? So we redefine, so what we do, what we have done in our work is, one of the work is to construct this reduced dynamics using the metric formalism properly, which in our knowledge has not been done. And we contrast it to the another usual way of defining a state, a reduced state, where we divide or redefine at each time. We redefine it by dividing it by the trace of your density matrix. Because remember, the unitary, non-unitary evolution will not preserve the trace, right? So at each point you will want to divided by the trace. While in the first scenario, where we are using the metric formalism, you don't have to do that, right? So the first one is a linear operation, and the second one is nonlinear. And this difference is important because, so there are the last two slides of my talk now. I'll just show you two graphs. First one is showing you the non-Markovianity of the reduced dynamics. As I said, the reduced coin dynamics will be non-Markovian because the interaction is strong. But how is that non-Markovianity changing when you are introducing non-hermiticity in the walk as a whole, right? For that, we redefine so non-Markovianity in this case is defined by the inability or some sort of a measure of information backflow, right? And you see that, so the dotted lines are, in this case, when we are not introducing the metric, we are defining it just by dividing it by the trace, the old method. And the metric method is the solid line. And one more thing that I would like to tell you, the walk operator is written right there. It's a two-step walk where the thetas are changing one after the other, the parameters of the coin by which we are rotating our coins, right? But then there is a loss gain functions where L1 and L2 are these functions which are giving you equal loss and gain in the two states of your coin. And they're dependent on this parameter gamma. And as you change gamma, you are changing the degree of hermiticity, non-hermiticity. And at one point, if you go beyond the limit, the PT symmetry will break down, right? And those points are called exceptional points. We see that the metric formalism actually identifies these exceptional points very well. The jumps that you see in the solid lines exactly happens at the metric, at the exceptional point where the PT symmetry breaks down. And this phase transition in the information backflow is not seen when you are looking at this dynamics through the other definition that we showed you, right? The nonlinear definition. And the second thing that we looked into was the entanglement between the coin and the position. As I said, the algorithms on which these quantum walk algorithms are based on these properties, the ballistic properties and all those things, they depend heavily on the interaction between the coin and the position space of the quantum walk, and how the entanglement between those two changes due to the noise outside is very important to these algorithms and simulation techniques also. So we see that as you introduce the non-hermiticity with the metric mechanism, you will actually, what we see is that, though this is not a mathematical proof, but it's a numerical indication that for the asymmetric cases, the entanglement entropy does not really change in the asymptotic limit, but for the symmetric walks, which go on both sides, it actually decreases. And we have, I mean, there are many other studies using this, but this is one of the graphs that I would like to show you. So this is, this will be my talk. Thank you.